All right, I guess we can get started. So today we're going to talk about what's significant in laboratory measurement and how to take measurements in the lab, how to do calculations with the lab, and how to do some of the data analysis when you have a lot of quantitative data, which you will have in the lab coming up when we do the Ellen Swallow Richards or the Charles River lab. One thing I wanted to point out, so there's handouts in the back. We're going to be going through how to do the calculations and how to do all the statistics. And there's an example problem that we're going to work through as we go in the back. So if you want to make sure you have a copy of that, that might be helpful. And one of the things that was pointed out this week in the lab is that in the lab there is a typo left over from when we were in the old labs in Building 4. And so this Wednesday and Thursday, the TA session that it says, the help session about how to write the Ferrocene lab report, is going to be in the lab, not in 4:30 as it says in the lab manual. So just come to lab as normal. The beginning of the lab period will be a quiz on the Ferrocene lab. So anything procedure-wise, calculations, reactions, all that good stuff, things that you should know having done the Ferrocene lab and hopefully having started to write up your report a little bit. And then after the first 20 minutes or so is going to be the quiz, and then your TAs will give a little bit of a lecture about what they're looking for in the Ferrocene reports. So that's a good time to ask any questions about if you're unsure about where to write anything, how to write anything up, if you have anything that you've already written and you want them to look at. They will be in the lab to help you out with that. And we have some more office hours too that got posted to Stellar, and I will have a slide about them at the end of this lecture too for more help. But yeah, day 4 of Ferrocene, come take the quiz, then get some help on your reports. It is in the lab, you don't have to go anywhere else, just come to lab as normal. Okay, so if we're going to be talking about measurement today, then we need to talk about what things you should be thinking about if you're going to measure something. So if you're going to measure the length of this piece of wood with this ruler, how long would you be able to say this piece of wood is?
There's no units.
There's no units. Yeah, that's a problem. What else is wrong?
It's not long enough.
It's not long enough. So what's the minimum we could say about this piece of wood? It's longer than one something. So this is not a great measuring tool. What about this? Any better? Slightly better. So now what could we say about the length of the piece of wood? It's between 1 and 2. Probably a little closer to 2, but we can't really say too much more about it than that, and we still don't have any units. So this is just to kind of get you thinking about what we need to be considering when we are choosing how we're going to measure something, and when we are recording measurements, what information we can reasonably get from the measuring tools that we're using. So to talk about measurements a little bit more, we're going to need to talk about some terminology and get this out of the way so that we're all using the same language. And you've probably seen these terms before in your other science classes in high school and middle school going way back. But to just as a quick refresher so we're all on the same page, precision is how close repeated measurements are to one another. So if you measure the same thing a bunch of times, you would like the results to be the same. And you've probably seen these bullseye diagrams where if the results are all really close together, that is very precise. And you can measure that with the standard deviation. So the standard deviation gives you an idea of relatively how close your points are to each other. Accuracy is how close a measurement is to the true value or the value that you actually are trying to measure. So if you are throwing darts and you are trying to get the bullseye, then if you have high accuracy, then you have them all in the bullseye. If you have a high accuracy and high precision, then all of your darts always go to the center. You can have high accuracy where you're always kind of around the target, but your points are scattered. And then you can have low accuracy and low precision where you're just all over the place. We measure accuracy by the percent error. So it's the error relative to the result that you're trying to get. And the answers don't need to be close to each other to be accurate. Like I said, they can be kind of spread out, but still all close to the target value. So these are some terms that you've probably heard. They're a little bit used differently in chemistry sometimes than you may use them colloquially, so we just want to go over that. More terminology. Absolute error is how far away a measurement is from the true or accepted value. So if you're trying to measure, let's see, with this here pipette, it has this pipette is designed to measure 10 milliliters, and you can look at it and it has a tolerance of 0.04 milliliters. So that's an absolute error. It is how far away your measurement will be from the true value. If you're trying to measure 10 and you measure 10.04, then your absolute error is 0.04 milliliters. So you just subtract what you got from what you intended to get. The relative error is how far a measurement is from the true value, but it's relative to the quantity that you're trying to measure. So if you've measured 0.04 or 10.04 and you intended to measure 10, then your absolute error is the 0.04. To get your relative error, you'll make it a percent and divide it by the 10 that you intended to measure. So now you have a 0.4% error. One way to think about this is if you have an absolute error of 1 milliliter when you're measuring out 2.5 liters of material, that's pretty small. But if you have an absolute error of 1 milliliter when you're measuring out 2.5 milliliters of material, then that becomes a much bigger problem. So depending on the quantity that you're measuring, sometimes it's a little bit more useful to report the relative error than the absolute error and vice versa, depending on the application. But if you say, yeah, I had an error of 1 milliliter, and your friends are all saying, oh, you did such a great job, and then you say, I was only trying to measure 2 milliliters, then not so great. Other types of error are random error and systematic error. So random error is things that we can't really control for or identify, and it causes data to fluctuate relatively uniformly around a mean value. And that's one of the things that's given on the uncertainty in the measuring apparatus that you're using. So this pipette measures 10 milliliters plus or minus 0.04 milliliters. That is a random or indeterminate error. The data will fluctuate around 10 milliliters within 0.04, you know that. And you can control for that using statistical analyses, which we'll talk about in a little bit. Systematic or determinate error is error that has a known cause. And that could be from faulty or poorly calibrated instruments, human error, or chemical behavior inside reactions. So if you intended to get 5 grams of product and you got less than 5 grams, then you know that there is some error associated with your experiment. And it could be because maybe some of your iron oxidized, or maybe you spilled some of your ferrocene, or maybe you were not tearing the balance every time you used it. So that'll introduce error into your measurement if you were using the equipment improperly. Or if you're reading from a burette and you're always reading in the wrong direction, or you didn't read to enough significant figures, that's systematic error. And so that's not necessarily from the glassware itself, that's from how you were using it. And these are types of error that you can talk about in your discussion section of your lab report. So you can talk about the error that is associated with the measurements that you can control and that you cannot control. So the last term that we need to talk about in terms of when we're making measurements or doing things in the lab is, what does it mean for something to be significant? So you may have heard of the term significant figures, or this is a significant result. What does it mean for a number or measurement to be significant, and what makes a measurement that we take significant in the lab? Yeah.
I feel like significant means like all of the numbers that you're certain about plus one estimate for like one final.
Exactly, yeah. So a number is significant, and you report the significant figures are, in a measurement, all of the numbers that you're certain of plus the first uncertain digit. So a lot of times you'll have some sort of, you won't have measurements every maybe 1/10 of a milliliter or 1 milliliter, depending on the size of the glassware that you're using. So you can be certain of some of the measurements, and then you are uncertain of others. So in our piece of wood, we were certain that it was bigger than 1, but we were uncertain of the next digit, so we could estimate that second digit, and that counts as significant. A quick review of significant figures and how to use them. All non-zero digits in a number are significant. Zeros in between non-zero digits are also significant. Zeros to the left of a non-zero digit are not significant. Zeros to the right are only significant if there's a decimal place, and you can avoid ambiguity in that with scientific notation. So if we just go through these really quickly, how many significant figures does this have? 4. 3. 6. 2, maybe. As written, yeah, you would probably call it 2 because the zero's to the right, but if you wanted this 0 to be significant, then you could write it like this, and now how many significant figures do we have? 3. And if the 0 is not significant, then to avoid people being confused about it, you could write it like this, and we have 2. So that's one way you can use scientific notation to get around ambiguity. Yes?
Yeah, I have a question. So for 590, if someone put a decimal point after the zero, would it be 3 significant figures, or would it be 2?
So that's a question that I've always gotten. I think just conventionally speaking, if you wrote something as like this, maybe. More conventionally correct would be to write it as 5.90 times 10 to the 2, because you don't usually have a decimal place if there's nothing after it. And then if you wrote it like this, though, then you have 4 significant figures, and that's more than you want. So just go with the scientific notation instead of having a hanging decimal place, because that's not a typical way to write numbers. When you're doing math with significant figures, if you're adding and subtracting, then your final answer should have the same number of decimal places as the number you started with that has the smallest number of decimal places. When you are multiplying and dividing, the answer should be rounded to the same number of significant figures as the number you started with that has the least number of significant figures. So when you are multiplying and dividing, you want to count up your sig figs, and when you are adding and subtracting, then you pay attention to your decimal places. So if we go back to our piece of wood, then using that ruler that we had earlier, we can estimate maybe this is 1.8, so we have gradations every 1 unit. We still don't have units, whatever this is, and then you can estimate this 1 digit past that. And then our uncertainty is our gradations divided by 2. So we know that we are within 0.5 of the correct answer because we can estimate that it's within this half of our interval. If we add more gradations to our ruler, so if we have markings every 0.1, still no units, then we can say with certainty that our piece of wood is 1.567, bigger than 1.7 and smaller than 1.8. So it's 1.7 something, you can estimate that last decimal place, and then your error gets smaller too, your uncertainty in that measurement. This is important in the lab because you need to make sure that you're choosing the correct apparatus for the amount of uncertainty that you want in your measurement. So if you see something in your lab manual that says measure 1.2 grams, then this balance is totally fine, because the balances, if you've never noticed at the top, they have the uncertainty written on there. So the uncertainty is in this last decimal place here. So if you want 1.2 grams, then you can get 1.2, and then your last digit is the uncertain one. You should always write down all of the digits that are on the balance screen. But when you're going to calculate uncertainty or do an error propagation, then you know that the last digit is where your uncertainty is. So this is plus or minus 0.01 grams. So we have 3 different types of balances in the lab, so you want to make sure that you're choosing the one that has the correct number of decimal places for the quantity that you are trying to measure. And the same thing goes for glassware. So the uncertainty in the glassware is frequently reported on the glassware itself, and there are standard tolerances for various sizes and grades of glassware. So if you've ever seen glassware that's volumetric, it may say either an A or a B on it. So the A is like the highest standard, and then B is a slightly higher tolerance. And there are standard things of those that you can look up, but it's usually written on the glassware. And so this is an example of the 10 milliliter pipette that I was showing you earlier. So you can look at the pipette, and then on the top part here, it'll say 10 milliliters, and this one says plus or minus 0.04. This pipette says plus or minus 0.02, so that one's calibrated a little bit more precisely. These are also 10 milliliter pipettes, and you can look on the top part here to figure out what their tolerance is. These are both 0.06. And one of the other things that you need to make sure when you are using different types of glassware is to figure out where the markings end. So these are both 10 milliliter pipettes, and they are designed to measure 10 milliliters within 0.06 milliliters. This one, I don't know if you can see it from here, probably not, but the maybe if I hold it up here, the markings, and they go from 0 to 10, and it ends here, and there are no more markings at the tip. So that means that the only time you're measuring something is when your liquid is within where the markings are. So if you're going to measure 10 milliliters, you need to start your liquid here, end it at 10, and don't go below that because that quantity is not calibrated. There are some pipettes, like this one, that are also designed to measure 10 milliliters, but these have gradations all the way to the end of the pipette. So to get 10 milliliters out of this one, you would fill it up to here and then drain it all the way out to the bottom. So you want to make sure that you check your glassware ahead of time to figure out how much of it you can use to measure liquids and what you get if you empty it all the way out versus measuring by difference. If you look at your graduated cylinders are different sizes, and the markings come in different levels of precision. So this has markings every half a milliliter, and its tolerance is listed at the top as plus or minus 0.3. The 50 milliliter graduated cylinder has markings every 1 milliliter, and at the top it'll tell you that its tolerance is plus or minus 0.5 milliliters. So again, just that's the 1 milliliter divided by 2 rule. So sometimes that holds, and sometimes it's a little bit different. Volumetric glassware always has a smaller tolerance, so this is to 250 milliliter volumetric flask, and on here it'll tell you that its tolerance is plus or minus 0.12. So you should always look at these, and when you are making measurements in the lab, when you're writing things down in your lab manual, you should always write down what the uncertainty in the measurement that you're making is. So whether it's on one of the balances or a volume, always make sure that you write down what the uncertainty of the glassware that you're using is. If you look at something like a beaker, this also has a tolerance on it, and it's plus or minus 5%. So that's a lot when you are looking at a 300 milliliter beaker. That's going to be a lot more uncertain than any of these other measuring implements. So it's good to know before you choose what piece of glassware you're going to use to measure something, how precise you want your answer to be, and how much uncertainty is acceptable in the measurement that you are making. With burettes, so this is a 50 milliliter burette, and it doesn't have a tolerance listed on it, but it has markings every 1/10 of a milliliter. So what would the uncertainty in a burette be, in this burette? So if the markings are in a 50 milliliter burette, the markings are every 0.1 milliliters, so the uncertainty is 0.05, so plus or minus 0.05 milliliters. In a 10 milliliter burette, the markings are every, let's see, I think they're every 0.2, no. What are these? 0.05? Yeah, these are every 0.01 in a 10 milliliter burette. So what would the uncertainty be here? Yeah. So make sure that you are looking at what glassware you're using and you record the correct number of significant figures, because it changes based on the type of burette, and even within different types of glassware, they are made different with varying levels of quality. So we can make one measurement, and then we can figure out what the uncertainty is in that one measurement. But what happens if we take multiple measurements and have to do math with them? So if you look at your worksheet here, this is an example of something that you might do in the lab where you have done a series of titrations to calculate the concentration of some sort of HCl solution. So the first question is, what is the uncertainty associated with a 50 milliliter burette? We already figured that out. And then if we were going to calculate the volume dispensed in each titration trial with the correct error, how would we do that? So one of the ways that you could think about adding up the error in these measurements is just straight up adding the error. So if you have, for this first example, we have 12.52 milliliters. This chalk is no good. And then do volume by difference, we have 0.24 milliliters. And each of these has an uncertainty of plus or minus 0.05 milliliters. Oh. So if we added up the error in these measurements, then we would get 0.1 milliliters. But it is probably pretty unlikely that both of these measurements were off by the full 0.05 milliliters. So this would tend to overestimate the amount of error in your final answer. So what we do is we propagate the error. And when you're adding and subtracting, you use the absolute errors because you should be adding quantities that have the same units. So units will be consistent throughout your calculation. And the way that we do this is, did anybody subtract this out? I don't know if anyone has calculated. Hopefully. Great. So if we subtract these two numbers, then we get 12.28 milliliters. And then how would we propagate the error for this calculation? So our error is going to be the square root of the squares of the errors of each individual measurement. So each one is so if anyone has done that out or can do it in their head or not, the answer that you get is 0.007071067. So that's a lot of extra decimal places. And what we really care about in uncertainty is where's the first decimal point that is uncertain? What is that first digit that we don't know for sure? And so we always round any error to the first significant figure. So the error associated with these measurements is just 0.07 milliliters. So to write this correctly, you would write it as 12.28 minus 0.07 milliliters. And you can calculate the volumes for each of those trials, and then the error for all of them is going to be the same because the error for each of your burette measurements is going to be 0.05. So then we can talk about what happens to the error in a calculation when you are multiplying or dividing something, which is this next part. So if you're going to use this value to calculate the concentration of the HCl in this fake experiment, then you'll have to do some multiplication and division, and you'll be using different quantities that have different units. So you can't just use the absolute error because they have different units. So if you have your error with your burette reading, that'll be in milliliters. If you have your error with your concentration, that's in molarity. So we can't use the absolute error, so we'll have to use the relative error, which, if you remember, is the absolute error divided by the measurement that you've made. So if you want to take a second and do out that calculation for how to calculate the concentration of the HCl, then we can do it all together in a second. And we'll just do it for the first trial, and then if you guys want to have more practice, you can do it for the others afterwards. So if we're going to set up this calculation for the concentration of the HCl solution, where would we start? It's the first thing that we have to do or to calculate in this. Yeah.
Figure out how much sodium hydroxide.
Yeah, in what units? Moles. So we can figure out how many moles of sodium hydroxide we have by taking our volume and then we have our units, our concentration, which are in moles per liter, so we need to turn this into liters. And then we can use our molarity to get moles. I guess we could do that as moles of NaOH in 1 liter. Then we can go from moles of NaOH to moles of HCl. What's our molar ratio? Too easy, 1 to 1, yep. 1 mole of and then we have moles of HCl, and then the last step is to divide by our volume of HCl, yes, which in this case is 0.0100. liters. That should give you, if anybody did it out, 0.060172 molar. Hopefully. So that's our concentration. And now we have to figure out what the error associated with that concentration is. So we will look at the error involved in each of these terms. So we have our error associated with our burette measurement. So our first one is going to be the 0.07 over 12.28 squared. Plus, what's the next error that we have? Which one? No, say it. The last one, yeah. We have error associated with this measurement, right? And the error associated with that is 0.02 milliliters. So you have 0.02 milliliters over your 10 milliliters. And then what's the last error that we have? Yeah. The concentration of NaOH, the 0.04. So you have 0.04 over 0.49. So that's how you will calculate your error for the concentration of the HCl. And if you do this out, you get 0.08. So then how would we report these two together? What's the thing from before? So what is this? What type of error, or what type of error is this? Is it an absolute or a relative error? Relative. So we calculated it from all of the relative errors. So this is a relative error, and it's also, you could think of this as like 8%. So in order to get it back into a standard error that we can report with our 6.60172, then we have to multiply these two together. And if we go back to our sig figs from before, in this calculation, how many significant figures should our final concentration answer have? 2. So this has 2 sig figs, so we'll round this to 0.60. Then you can multiply that by your 0.08 relative error, and your final answer should look something like this. Ooh, way down here. 0.60 plus or minus 0.05 molar. Any questions about calculating errors and doing error propagation? So this is why it's important to make sure that you have the correct tolerances and the correct errors associated with all of your measurements, because when you go to do all of your calculations and write your lab report up, it will be very hard to figure out your error if you are missing some. Okay. So now that we know how to deal with the various independent measurements, what happens when we make the same measurement more than once? And this goes back way probably to like middle school when we talk about the mean or the average of a sample. So in statistics land, they call all of the possible values that you could measure of something the population. And it's really hard to know the true mean of the population unless you have access to the entire population and you've taken all possible measurements, which is pretty much impossible, especially in the case of 5310. We're not going to be making all of the possible measurements there are for each quantity that we measure. So in the lab, we can take the mean of a subset of the population, we call that the sample, and then calculate our sample mean. So a population mean, if you ever see in statistical literature, is denoted as mu, and then our sample population is denoted as the x bar, where you just add up all of your measurements, divide by the number of measurements you took, and that's your mean. So if we calculate an average or a mean for the HCl solution on the back, if you didn't do the calculations from before, the concentrations that you should get are 0.60, 0.61, 0.61, and 0.64. So if you add all those up and divide by 5, then your mean concentration is 0.615, or rounded to the correct number of significant figures, 0.62 molar. The other thing that you can calculate is the standard deviation of your measurements. And so remember, that's a measure of precision or how close all of your measurements are to one another. So small standard deviation means that all of your measurements are very close together, very precise. And to calculate the standard deviation, again, you could calculate the standard deviation of an entire population. That's the sigma up there, and then you need to know your population mean. But in the lab, we are taking a smaller subset of the population, so we have to calculate a sample standard deviation, which is denoted as S. And the major difference here is that instead of dividing by n, which is the number of samples, you divide by n minus 1. So the number of measurements you took minus 1. So to calculate a standard deviation, you calculate each of your measurements, subtract it from the sample mean, square it, add those all up, divide by n minus 1, and then take the square root. And you can do this on a scientific calculator, graphing calculator. Excel does it for you. Any statistical program that you want, you don't have to calculate this by hand. In your lab manual or in your lab report, you can just show the formula for it, and then you can calculate it using any sort of statistical program. So if we calculate the standard deviation for our concentration of the HCl solution, then you should get, I'm not going to do this all out by hand right now because we don't have a lot of time, but if you wanted to try it out later or check your answer for somewhere else, it should be 0.1732, it keeps going. So the standard deviation is typically rounded to the same number of significant figures as the measurements that you are using to get the standard deviation. You'll see it reported pretty frequently like that, so we can report our standard deviation as 0.017. Since we are taking a mean that is not the population mean, we know that we may not have exactly, the mean of your sample will probably not be exactly the same as the population mean. But you can figure out how good of an estimate your mean is of the overall population mean by calculating the standard error of the mean. And that is done by taking the standard deviation of your sample and dividing by the square root of the number of data points that you have. So if you want to get a better and better estimate of the true mean of your population, then you can keep increasing the n value, and eventually it'll make your standard error smaller. To a point, since it's the square root, once you get a big enough number of n, then incrementally you get less and less benefit from adding more and more data points. But you can also make your standard error smaller by decreasing your standard deviation. And so if you can make more precise measurements, then that will also help improve the quality of your mean and how accurate it is toward the actual population mean. All of this is kind of leading up to doing statistics. And all of statistics is essentially based on the Gaussian distribution or the normal distribution, and you've probably seen this before. And this graph is an axis of where the x-axis is the number of standard deviations away from the mean, and then the y is the probability of finding a measurement in that space. So you can see that the highest probability of all of your measurements is going to be very close to the mean. So if you're taking measurements accurately, they should be very close to the mean. And then as you get further and further away, there's less probability that some measurement you take will be 3 standard deviations away from the mean, and so on. So this number z is calculated by subtracting your number from the mean and dividing by the number of standard deviations. So it's just essentially the number of standard deviations away from the mean your measurement is. Oh, back up. We cannot go back. There we go. One way that we can use this is to figure out confidence levels of the measurements that we take or the means that we calculate. And so you can kind of do an error under the curve analysis here, or an area under the curve analysis. And so for all measurements that are within 1 standard deviation plus or minus from the mean, that accounts for 68% of the area there. If you go within 2 standard deviations, you can say within 95% confidence that your mean is within that area, and then within 3 standard deviations plus or minus, there's a 99% chance that your mean is within that area. So we can use this when we are calculating the accuracy or how confident we are that we have measured the population mean with the samples that we have taken in the lab. We can do this because of the central limit theorem, which states that the distribution of sample means in a population will constitute a normal distribution, even if the population itself is not normally distributed. So if you take a bunch of samples or take a bunch of measurements in the lab, then you can use the normal distribution to statistically analyze them, even if you don't know the distribution of the population itself. So we can use that information to calculate confidence levels of a mean that we calculate. So what that means is we can calculate how confident we are that our mean falls within a certain range of the actual population mean. And you can say it with different levels of confidence. You can say I'm 99% confident and you'll get a wider range, or 95% confident and you'll get a little bit of a smaller range. And the range of the values is what we call the confidence interval. And you can calculate a confidence interval for the actual population mean, and that is your standard mean, that z-score that we were talking about, times the standard deviation of the population divided by the square root of n. To use z, as in the previous slide, you need to have a big enough sample size that your estimates of the mean and the standard deviation are a good enough substitute for the actual sigma, the population standard deviation. That's really challenging in lab situations, and in 5.3.10 we will not ever have a big enough sample size for that to be the case. So as an alternative, we can use the t-statistic. So to calculate a confidence interval for a mean that you calculate in lab, you can take your mean plus or minus the t-statistic times your sample standard deviation over the square root of n. And you can calculate t-statistics using this formula if you have all of this information, or you can get a table of t-values for varying confidence levels and varying degrees of freedom, which is n minus 1, which is so the number of measurements that you took minus 1. So if we're going to calculate a confidence interval for the mean of our HCl concentration, then we'll have something like, we need our average plus or minus TS square root of n. And you'll notice that this standard deviation over the square root of n is the standard error of the mean. So if you calculate that, then it'll make it slightly easier to calculate your confidence interval. And so to do that, we're going to need some sort of t-table, which gives you the t-statistics. Our average of the mean was 0.62 plus or minus. So the t-value, if we have 4 measurements, then our degrees of freedom is going to be 3, so n minus 1. And then we want to use a two-tailed t-test because we don't know which way our measurement is going to vary. So the two-tail means that it could be higher or lower than the actual mean. So you want to calculate one that has a value of 0.05, so that'll be corresponds to the 95% confidence interval. And 3, so it's 3.182 is our t-value. And then times 0.017. And what you get if you do that out is so when you're going to report your 95% confidence interval, you would add this number and subtract this number from your mean and then report it as a range in parentheses. So 0.593, 0.647. And so that's your 95% confidence interval. And so what that's saying is that there is a 95% chance that the actual population mean lies between these two numbers. You are 95% sure that the actual mean is in there. So in your lab reports, when it says to calculate a 95% confidence interval, that is what we are looking for. Other issues you may run across in your data is if you take repeated measurements of the same quantity, you may have outliers. And sometimes you can look at your data and say, wow, there's definitely an outlier here. And other times, but even if you can do that, it's nice to be able to mathematically demonstrate that it is in fact an outlier. And so to avoid subjectivity in whether you're tossing out data points left or right just to make your stuff look better, you can use the Q-test to help decide whether a value can be kept in a data set or should be rejected as an outlier. And the way that the Q-test works is you take the absolute value of the result that you're worried about, the questionable value, subtract it from its nearest neighbor. so whatever the next closest value that you measured was, and then divide it by the spread of the data, which is just your highest value that you measured minus your lowest value that you measured. And then you have to look at another table of standardized Q values, and if the Q that you calculate is greater than the Q in the table for the number of data points in the confidence level that you want, then you can reject that point as an outlier at that confidence level. So the last question on here is not really related to the first whole set of problems, but if you took the following measurements for a concentration of an NaOH solution, are there any outliers in that data set? So what's our Q calculation for this data set? Which result might be questionable? 2.86, yeah, that seems to be a little bit higher than everybody else. So our questionable result is 2.86 minus 2.52 is its next closest neighbor, divided by how do we calculate the spread of our data? So 2.86, which is our max, and our minimum is 2.38. So if you do that out, you get 0.34 divided by 0.48. So our Q value is 0.708. Now if we look at a table of values for our Q test, so we can either calculate it at 90% confident that it's an outlier, 95% confident that it's an outlier, and all the way down. So if we wanted to calculate at 95% confidence level that this point is an outlier, then we had how many data points in this data set? 6. So we would look at 6, 95%, our Q value is 0.625. So 0.708 is greater than 0.625. So is it an outlier or not? The Q that you calculate is bigger than the Q in the table, then it is indeed an outlier, and we can confidently say that that does not belong in our data set. Ooh, we're working on it. Come on. So you can see that if anything had changed, like if we had had fewer data points, then it would not be an outlier. Or if you wanted a higher confidence level, then it also would not have been an outlier. So it's a little more strict how far away from the rest of the points it has to be before you can call it an outlier. The last thing we're going to talk about is doing a least squares regression. You'll make a bunch of calibration curves when you are doing different measurements with UV-Vis spectroscopy. So in UV-Vis, which you'll talk about in the next couple of labs, the absorbance of a sample at a certain wavelength, how much light it absorbs, is related to its concentration. And this is a calibration curve with the concentration of bovine serum albumin protein versus absorbance, which you guys will be making a similar one in the catalase lab coming up. So it assumes that one variable is known, so that's our concentration, that we have known concentrations, and that all of the variation in the y-axis is linearly related to our x values. So that's one assumption that you have to have before you're going to make a least squares linear regression. The way that you can calculate all of the values in a least squares regression, which the whole idea of is to get an equation for a line in the form of y equals mx plus b. So that's the point of all this. And you'll have different points, and you want to calculate a straight line through all of your points. So some of the terminology that is associated with this is the residual value. And so that's your vertical distance between a point and the line of best fit. So this is your residual value. Each point has a residual value. And the way that the line of best fit is generated in the least squares method is they take the square of all of these residual values and try to minimize it. And so you can calculate various quantities. If you take all of the x values, subtract them from the average x and square them, then you'll get the SXX. You can do the same thing with the y values, and then the x and the y values. The slope of the line is this value over this one. To get the y-intercept, you take the average y, subtract it from the slope and the average x. And then the r-squared, this was a misprint in your slide handouts. It should be 1 minus this quantity. In the handouts, the 1 is not on there. And so the r-squared value, which you've probably seen before, is the coefficient of determination. And that is a measure of how well this best fit line can explain the variation in y in a linear fashion. So essentially, how well do your points fit a linear relationship? Is that a good way to explain your data? So the best way to generate this is in Excel. You could calculate all those quantities by hand if you want to, but Excel will do it for you, or your other favorite mathematical software program. You graph your points as an XY scatter plot, then you can right-click the data points and it'll say add trend line, and then you can have options to display the equation and the r-squared on the graph. So you'll get your y equals mx plus b equation there and your r-squared value there. So you can see that this line this is not a very linear set of data, so your r-squared ideally is close to 1. And this is close-ish to 1, but that is definitely not a linear relationship. You can get it higher than that. And we'll talk about that more when you guys make your calibration curves for the bovine serum albumin. The Kumasi blue dye is only linear in certain regions of the calibration curve. So you'll have to calculate different lines for different pieces of the curve, depending on what your concentration is. The last thing that we can do to get more information out of a set of linear data is to use the Linus program in Excel. And if you've never done this before, you type in your data as a series of x and y points, and then instead of graphing it, well, you can graph it too, but in addition to graphing it, you highlight a 2x5 area of empty cells. And while that's highlighted in the first cell, you type in equals Linus, and then it'll prompt you to highlight your y values, then highlight your x values, and then you can type true and true. And what that'll do is, if you type false, it'll set the y-intercept to 0, and we don't want to force our lines through 0. So you will have your slope, and then if you press Control-Shift-Enter, even on a Mac, so on a Mac, press Control, not Command, press Control-Shift-Enter, and it'll give you this array of data. Once you get this array of data, don't try to change any of these values, or Excel will get kind of mad at you. So just leave it. And this is the key to what each of the cells is telling you, because it won't give you this information. You can look it up online, or it'll be on these slides. So your first thing, it'll just give you your slope and your intercept, and then it'll give you, these are the two that we care about the most, are the standard deviation of the slope and the standard deviation of the y-intercept. So sometimes in this course, you'll make graphs where the slope is representative of a certain quantity, or the y-intercept is representative of a certain quantity if you're graphing any equation in linear form. So then you'll have the standard deviations of each of those measurements. Then it'll also give you your r-squared and a bunch of other information that you want if you're doing different statistical tests.